This is lesson number 3 for engineering dynamics. In this tutorial we will look at the normal tangential coordinate system, so normal tangential coordinates. The tutorial contents includes an introduction to circular motion. We will look at the normal tangential coordinate system and we'll complete 3 example problems. So let's continue on. So let's say this particle is located at this particular point along this circular path, and that circular path has a radius of 1 meter. Okay, so because it's a circular path, the radius is going to stay constant, and all the radius is just the distance from the center of the circle to where the particle is now. Okay, so the distance from the center to this point here to the actual edge of the circle is the radius. And let's say after 1 second the particle ends up there. We're also going to say that the radius there is also 1 meter, because remember, the radius is constant. Okay, so any circular motion that occurs, okay, any circular motion, the radius is always constant. That's a really important point. And let's say that the curved distance that it moved from 0 seconds to 1 second, okay, let's say that distance there is also 1 meter. So this curved distance there is equal to the radius. If that's the case, then the angle that's subtended by that arc here is going to be 1 radian. So that is 1 radian. If we draw the angle between these two lines, theta, and the distance along that curve is the same distance as the radius, the angle is going to be 1 radian, where 1 radian is equal to 57.3 degrees. So we say d theta dt is going to be theta dot. Okay, so theta dot is just the angular velocity of the particle. Okay, so how many radians per unit time does it displace? Okay, so in this case, in 1 second, it's covered 1 radian. So that means we can say that the angular velocity is 1 radian per second, or we can write it like this, okay, 1 radian per second. So therefore we can say theta dot equals 1 radian per second, and that is the angular velocity. Sometimes theta dot is written as omega here. Sometimes it's given this symbol here, but this symbol is usually used for frequency. Okay, so frequency would just be the number of full revolutions per second, and whenever we're talking about frequency, we use the symbol omega. So let's say this distance here along the curve, okay, we're going to call that S. Okay, so that distance there, I'm going to call S. So that curved distance is S, and to get S, we do R times theta. Okay, so remember, if it's 1 radian, if there's 1 radian between these 2 points here, if the angle's 1 radian, that means that the curved distance there is going to have the same distance as the radius. And then if we differentiate this with respect to time to get ds dt down here, and we differentiate theta with respect to time, so we get d theta dt. We don't differentiate r with respect to time because r is just constant. R doesn't change with time. Okay, so we just leave r as it is. And then we can rewrite this like that. Okay, so we can say ds dt equals v. So this is the velocity along the curve. And d theta dt, well, that's theta dot. Okay, so we just replace this with theta dot. So we get v equals r times theta dot. So the velocity equals the radius times the angular velocity. Important point to note as well is that velocity is tangent to that circular path at every point. This was discussed briefly in the previous tutorial, but as a reminder, velocity is always tangent to the path. So after a second, it's going to end up at this point, so another radian is subtended by that arc. Okay, so that's at 2 seconds, so another radian's gone by, then another second, another radian's gone by, and so on. Okay, if we wanted to calculate the speed of the particle along this circular path, we would just do the radius times its angular velocity. So we know the radius was 1 meter, and we know the angular velocity was 1 radian per second. If we substitute that in, we get 1 meters per second. In case you're wondering what happened to the radians, okay, so if we substituted radians per second into there, you might think we'd get meters radians per second, but we don't, okay, and that's because a radian is a dimensionless quantity. To calculate a radian, you just do the curve there divided by the radius. Since they would both be in units of length, those units of length would cancel out, leaving a radian as a dimensionless quantity. Some mistakes that I have seen is thinking that velocity is meters radians per second. It's not, it's going to be meters per second. So let's say the particle was still at this same position here at 0 seconds. And let's say a second later it then ends up at this point, so it's covered half of that circle. And there's our distance s, and the radius is still 1 meter. That would mean this time that theta is going to be pi radians, which is 180 degrees. We would then say that the angular velocity is going to be pi radians per second. So the angular velocity is pi radians per second. And if we wanted to calculate that curved distance, this time we would just do s equals r times theta, where r is 1 meter, and we knew theta was pi. So if we multiply them, we get 3.14 meters. So the distance along here would be 3.14 meters. And let's say if we want to calculate the velocity, so again, we apply this equation we got previously, and the velocity comes out as pi meters per second. Or we could have said 3.14 meters per second. And after 2 seconds, the particle is just going to end up back there again. The angular velocity for this would be pi radians per second, and the velocity of the particle along the curve is pi meters per second. Okay, so let's see what happens if we double the radius. So let's say r this time is 2 meters, and it started off from this position at 0 seconds and ended up there after 1 second, so it's covered half the circle. Okay, so now we're just doubling the radius. The angular velocity would still stay the same. Okay, the angular velocity doesn't change with radius, it stays the same, because the angle between these two lines would still be pi radians no matter how big you made the radius. So theta stays constant even if you're changing the radius. So again, we would still say that theta dot is pi radians per second, and the curved distance this time is going to change. So we get s equals r times theta, and we knew r was 2 meters and theta was pi. So we times them, we get 6.28 meters. So the distance along the curve has doubled. So if we double the radius, we double the distance that is travelled along that curve. Okay, but theta is unchanged. So if we want to calculate the velocity, we do v equals r times theta dot, where r was 2 meters, where theta dot was pi radians per second. So if we put that in, we just get 2 pi meters per second. So the velocity has doubled because it has to cover double the distance in the same amount of time. So that would mean the velocity would have to double. So let's say r is 1 meter again. Okay, so we brought the radius back down to 1 meter. Now we're going to talk about the angular acceleration. So if we take d theta dt equals theta dot, if we differentiate d theta dt, we get theta double dot. Okay, so the 2 dots there tells us 2 time derivatives. And that is the angular acceleration. We can also say the angular acceleration is alpha. Okay, this is a number symbol that's used for that, but I'm going to stick to theta dot. And the units of that would be radians per second squared. Okay, so radians per second per second. Okay, so that is the rate of change of the angular velocity. Let's talk about the acceleration along the curve. Okay, so if we remember, we said s equals r times theta, where s was the distance along the curve and r was the radius. And then if we differentiate that, we got the velocity equals r times the angular velocity, d theta dt. And then if we differentiate this again, we get this. So the time derivative of ds dt equals r times the time derivative of d theta dt. Okay, and we can rewrite that as d2s over dt squared. So that's this term rewritten to this. Okay, and we know that d by dt of d theta dt was theta double dot. So we can rewrite that like this. So I can simplify this as just a sub t, which means the tangential acceleration. Okay, so the tangential acceleration occurs along the path. Okay, and that's equal to r times theta double dot. And the units of that would be in meters per second squared. And that is a sub t there, so it's tangent at every point. So here's all the equations that we found. So we know that theta equals theta dot times t. We know s was r times theta. We know v equals r times theta dot, and we know the tangential acceleration a sub t equals r times theta double dot. So if we take these equations that we got from the first lesson in rectilinear motion, we know that these equations describe motion in a straight line. So we're going to apply this, but just along a circular path. So what I can do is take this first equation here and substitute v, okay, into here. Okay, so if I do that, I'll get this. So I substituted v there with r times theta dot, and I got this here, and then I substituted it into there as well, and then just changed the subscripts, and then I substituted a sub c, which means constant acceleration, okay, with a sub t, tangential acceleration, so I just substituted that into here to get this. I do the same thing here, so I substitute s with r times theta to get this, and I substituted that into there as well and changed the subscripts. Substitute v again, so I substitute a sub c with a sub t, and I get this. And then I do the same thing here, make those same substitutions into this equation, I get this. Okay, so you can see here that r is going to cancel out in this equation here. So r is going to cancel because it's on both sides. So they're going to cancel out. On this side, they're going to cancel out again. And then if we was to distribute this r here into those brackets, we'd have r squared there and r squared there. And we have an r squared here and an r squared there. So that means, again, they all cancel out again. So we're going to be left with these equations here. So this is how we describe motion on a circular path. We can just use when theta double dot is constant. But if we know theta double dot as a function of time, we can substitute that into there again. So if we were to compare these equations with rectilinear motion and for circular motion, we can see they're quite similar. So this is just in a straight path and this is along a circular path. However, with these equations, we can also apply these to a curved path. Okay, so let's talk about acceleration some more. Okay, so we know that when a particle moves along a curved path or a circular path, we know that the tangential acceleration a sub t is going to be just one component of its overall acceleration. Okay, so this is just one part to acceleration. So let's say v is constant along that curve. Okay, so this particle is moving up along this circular path with a constant velocity. Okay, so if it gets to this point in a time delta t, it displaces an angle of delta theta. So remember, v is constant, so velocity is constant along that circular path. And then we put in delta s there, which is the distance from where it is now to there. So that's just the change in distance. Okay, so we approximate that with a straight line. And remember, we're saying a sub t, so the tangential acceleration, which also acts tangent to the circular path, that is going to be 0. So the tangential acceleration is 0. And then if we take these two vectors here, join their tails together and draw in delta v, we get this. Okay, so there's delta v there. So if I take the two lengths for the radii and the length for delta s and use those to construct this triangle here. So these two triangles are similar. Okay, so the triangles are similar. So the ratios between their sides is going to be the same. So what I mean by that is delta v divided by v is going to be equal to delta s divided by r. And we also know that delta s is going to be v times delta t. So I'll just write that in there. So delta v over v is going to equal to delta s over r. And if I substitute delta s into here, I'm going to get this because delta s was equal to v times delta t. So if I carry on, and then if I multiply both sides by v, I'm going to get this. Okay, so delta v equals v squared times delta t divided by r. And then if I divide both sides by delta t, I can then get this equation here. So this is the average acceleration. So this acceleration only occurs because of the change in direction of the velocity vector. So even though the particle isn't actually speeding up along the circular path, it's changing direction, which means that it's accelerating. Okay. So if I then take the limit as delta t approaches 0 for delta v by delta t, I get dv dt, which is equal to v squared over r. And I'm going to call that a sub n, where this is the normal acceleration, because this acceleration vector acts normal to the radius of curvature, where the radius of curvature for a circle will just be the radius. So that means I'm going to say a sub n, the normal acceleration, equals v squared over r, and that is called the centripetal acceleration. Okay, so along the circular path, if the particle is moving with a constant velocity, a sub n, so the normal acceleration, is acting towards the center of curvature, where the center of curvature in this situation is r, and that is constant. So as the particle travels around that circular path, a sub n is always acting towards the center. So then I add that to my other equations that we got. Okay, so another way we can look at that is if we say that the particle is located at this point here, a radius from this fixed point O, so from the center of the circle there, okay, and we draw this horizontal line here, we can say that the angle between this horizontal line is going to be theta dot times t. Okay, so I just got that from here. So theta dot times t equals theta. Okay, and theta is the angle in radians between r and this horizontal line. As the particle moves along that curve, theta is going to increase, and it increases with time. So as time goes on, okay, the angle is going to increase, but theta dot is going to stay constant. So I can define the particle's position at this point as a horizontal distance, which I'm calling r times cos theta dot times t. So I'm just using r equals cos theta, but I've just substituted theta with theta dot times t. Okay, so that's its horizontal distance here. And then I can define the vertical distance as r sine theta dot times t. Okay, so I've just defined its position. And as this particle starts to rotate, these lengths start to change. Okay, so let's say if the particle got to this point here, this is going to get smaller and smaller, and this is going to be at a maximum. And then as it rotates around to say down here, this is going to be 0, and this is going to be a maximum again when it's at this point, but this time it will be negative. And let's say if it ended up there again, okay, so let's say the particle was here, then this is going to be a maximum, and this is going to be 0. But this is just one instant in time. So that means we could write r in vector notation as r equals r times cos theta times t in the I direction. Okay, so the I direction is here, plus r times theta dot times t in the j direction, where the j direction is in the vertical direction. Okay, so these are just unit vectors in the horizontal direction I and the vertical direction j. Okay, so if I differentiate this, if I differentiate each term, I'm going to end up with this, because the derivative of cos is going to give us minus sine, so that's how we get the minus there, and whatever the coefficient is of t, wherever the coefficient is, we bring that out. And for this one, we're just going to get the derivative of sine as cos, and again we bring out the constant coefficient out. And then if I differentiate this again to get acceleration, okay, so the derivative of minus sine is going to give us minus cos, and again I take out another coefficient from here to get theta dot squared, and the derivative of cos is going to give us minus sine, and again I take out the coefficient and put it there. Okay, and that's how I get theta dot squared there. So what I can do next is factor out a minus theta dot squared from each term, okay, to get this down here. And because I know r is equal to this, and if we look down here, we've got r times cos theta dot times t in the I direction plus r times sine theta dot times t in the j direction. This is the same as r, okay, so I can substitute r into here to get this. Okay, so I've got this minus sign there, and that minus sign is telling us that the normal acceleration is pointing towards the center. So that means I can say a sub n, our normal acceleration or centripetal acceleration, equals minus theta dot squared times r. And that, the magnitude of this, is going to be equal to v squared over r. Okay, so these are our two expressions for the centripetal acceleration, so a sub n. Okay, so we've got a sub n equals minus theta dot squared times r. We've got a sub n equals v squared over r. Okay, so these two are equal to each other. Okay? However, this minus here is just telling us that the centripetal acceleration or normal acceleration, calling them different things, okay, but called either the normal acceleration or the centripetal acceleration, okay. The minus is just telling us that it's acting towards the center, okay. I can say now that the magnitude of a sub n is just going to be theta dot squared times r. So I'm ignoring the direction, I'm just taking its magnitude, okay, and the magnitude is just theta dot squared times r, and same thing here again, okay, so the magnitude of a sub n equals v squared over r. And remember, it acts towards the center. Okay, so if I have the particle at this position here on this circular path, as it goes round, a sub n is always acting towards the center. In this situation, because it's a circle, the center of curvature is constant, so r is constant. If r was varying, at every point along that curve where r is varying, the centripetal acceleration would always act towards the center of curvature. Okay, so not forgetting that we also have the tangential acceleration as well, and that is acting tangent to the path that the particle is moving along. The tangential acceleration is equal to r times theta double dot, where theta double dot is the angular acceleration, and that is in radians per second squared. We've got the centripetal acceleration, we can write as v squared over r, or we can say it's theta dot squared times r, where theta dot is the angular velocity. We can also draw in a. Okay, this is what we was talking about in the second tutorial at the beginning. So a is just the resultant of these two acceleration vectors here. So a sub n and a sub t. We just apply Pythagoras to a sub n and a sub t, and that will give us the magnitude of a. And again, when the particle moves along that curve, a sub t is always tangent to the path, a sub n is always acting towards the center, and a is neither tangent or normal. So as it moves around, it stays in that same configuration. So this is going towards the center, this is tangent to the path, this is in between, this is always at an oblique angle, so it stays in that configuration. So this is a summary of all the equations that we have found. Okay, so make sure you write these down. These are important for you to know. So now we've had an introduction to circular motion. We are now going to talk about the normal tangential coordinate system. So again, if we take our circular path here and we draw in R, which is the radius, and the particles located at this point down here, we draw in these two unit vectors. Okay, so I've drawn two unit vectors. One is called u sub t, okay, which is a unit vector of magnitude 1, which is pointing tangent to the path. And I've drawn another unit vector, u sub n, which is acting normal to the radius of curvature. So these are just unit vectors, so that means their magnitude is 1. So we knew from before that a sub t acts tangent to the path. So if we multiply a sub t with this unit vector here, we'll get its direction, and so does v as well. So v also acts in the direction of u sub t, and a sub n is acting in the direction of u sub n. Okay, so a sub n, the centripetal acceleration, is acting in the direction of u sub n. And if we remember from before, we said a sub n equals v squared over r, which we can also say is theta dot squared times r. A sub t equals r times theta double dot. So that means we can write a in vector form as a equals a sub n times the unit vector u sub n plus a sub t times the unit vector u sub t. So this is just a written in vector form, where the unit vectors this time is u sub n and u sub t. And if we take the magnitude of a, we just apply Pythagoras of a sub n and a sub t. And if we write v in vector notation, we'll get 0 multiplied by the unit vector u sub n, because there's no velocity in the normal direction, plus v times u sub t. Okay, so velocity times the unit vector u sub t is tangent to the path. Okay, so that is velocity written in normal tangential coordinates, and this is acceleration written in normal tangential coordinates. So this would be a scalar quantity here if we wanted to get the magnitude of a. So we can also write a in vector form like this. So if we just substitute a sub n into here, we get that. So all I did was substitute a sub n into there to get this, and then substitute a sub t into here to get that. So this is a written in vector notation again. Okay, or we could have written like this, where v squared over r equals theta dot squared times r. So I could just put that down there as well. And also, if we wanted to find what angle a makes with u sub t, we'd just apply this equation here. So tan theta equals a sub n over a sub t. So that is the normal tangential coordinates. So basically what you need to know is that the normal tangential coordinate system is defined by these two unit vectors here, so u sub t and u sub n. So that is the normal direction and the tangential direction. In the tangential direction, we have this acceleration here, which is r times theta double dot, and we've got velocity as well. And we could have also written velocity as v equals r times theta dot as well, but we haven't written it here. And in the normal direction, we have this acceleration. Okay, so v squared over r, or theta dot squared times r. So let's say the radius of curvature now is varying. Okay, so this curve here is defined by a function y equals f of x. So this is just a general expression for that function, but it produces this curve where the radius of curvature is varying at every point. So let's say if we have a particle at this point here, and we draw in its radius of curvature. Okay, so that is going to be normal to the path line at this particular point. So I've just drawn in the radius of curvature, and I'm calling that rho this time, okay, to let us know that it's a radius of curvature at a particular point. We usually use the symbol r if the radius of curvature is constant, okay, but in this situation I'm using rho, and I've also drawn that circle around it as well. So let's say the particle moves from this point to another point here, for example. The radius of curvature is going to be different. So because it's slightly more curved over here, the radius of curvature is going to be slightly smaller. And then as it starts to curve more and more, the radius of curvature gets smaller and smaller. So our equations this time can be written like this. So we've got a sub n equals v squared over rho this time, equals theta dot squared times rho. And we've got a sub t equals rho times theta double dot. So this would mean at every point along this curve, a sub n and a sub t are going to be different because the radius of curvature is changing at every point. Okay, and then if we wanted the magnitude of a, again we apply Pythagoras to a sub n and a sub t. And also not forgetting that v and a sub t are tangent at every point. Okay, so tangent to the path line, and a sub n is normal to the radius of curvature. So that's drawn at every point. A at this point down here is going to be slightly more towards a sub t because the radius of curvature would be much bigger. So the bigger the radius of curvature, the smaller the normal acceleration is going to be. So let's say if the velocity along that curve is constant, at this point here a sub n is going to be at its minimum, and at this point here it's going to be at its maximum because this is the smallest radius of curvature. So the smaller it is, the bigger it's going to be, and the bigger it is, the smaller it's going to be. So let's say if we want to find what the radius of curvature is at a specific point, and we know the function y equals f of x. So the only thing I know is just the function y equals f of x, and I'm trying to find the radius of curvature at a certain point on the x-axis. So in order to do that, I'm going to draw another point up here, slightly ahead of this point, and I'm going to join that point with this line here, and I'm going to call the angle between them theta. So I'm going to define the position of this particle as P1, so it's got a position on the x and y axis, and P2 is going to be this point here, which I'm going to call x prime on the x-axis and y prime on the y-axis. So that's going to look like this. Okay, so position P1, okay, P1 is at a distance x along the x-axis and a distance y. Okay, so x, y, and the position of this one is P2, x prime and y prime. So, okay, so x prime, y prime. So I can also put in delta y. Okay, so delta y is going to be y prime minus y, so that'll be delta y there, and delta x is going to be x prime minus x, where delta x is this length here. And I'm also going to put in delta s. Okay, so I'm going to join P1 and P2 with this straight line and call that delta s. So that straight line is just an approximation for the curved distance going from P2 to P1. So that means I can say delta s equals the average radius of curvature times theta. Okay, so we've seen this equation before. That is the average radius of curvature, so that's supposed to be a horizontal line on top. So if I just draw that in, and then I can rearrange this equation to this. Okay, so the average radius of curvature from this point to that point is going to be delta s over theta. And then I can construct this triangle out of delta s, delta x, and delta y. Okay, so I can construct this triangle out of those. Okay, so if I take that circle now, and let's say that is a perfect circle, and I put my point there as well, and I'll draw these two tangent lines. So these two lines are tangent at each point. Okay, and this is a perfect circle. That means the angle here, theta, between this red tangent line and this green tangent line, that is going to be equal to this angle here. Okay, but we can't say the same for this situation because the radius of curvature going from this point to that point isn't constant. So I can't say theta is equal to this angle here between this tangent line and this tangent line. And the reason for that is because the radius of curvature is changing. But if I wanted to find the angle, so in this situation here, if I wanted to find what that angle was, all I'd need to do is just calculate the gradient, where its gradient is going to be its change in the y position divided by its change in the x position, and then if I do inverse tan of the gradient, that will give me the angle. But I can't do the same thing here. But the only thing I can do is use that trick from calculus by making delta x approach 0. So if I make delta x approach 0, and then if I want to find the gradient of that line here, so that red line, okay, I'll get this. So the gradient of that line is dy dx. So as delta x approaches 0, I can say the angle between those two lines here and these two lines here are going to be the same. Another way you can see it is as delta x starts to approach 0, this red tangent line starts to overlap the green tangent line, okay, and the angle between them would be 0, and at that instant the angle between these two lines would also be 0. Okay, so that means I can say theta between these two lines and these two lines are going to be equal, but to find theta between these two lines I just find the gradient, which is dy dx, and then do inverse tan of that where I'm treating dy as the opposite and dx as the adjacent. So now there's our expression there for theta. So now if I take all of this, okay, I can use this to then find my radius of curvature at a point. So again, this is the average radius of curvature. So let me draw that in again. And then what I can do is rearrange this equation for the average radius of curvature. And then I can rewrite it like this. So I can say delta theta by delta s equals 1 over the average radius of curvature. So I'll just flip this over. Okay, so I flip this side to get that. And then whatever I do to one side, I do the same to the other side. So I get 1 over the average radius of curvature here. And then if I take the limit as delta s approaches 0 for delta theta by delta s, I get d theta ds equals 1 over rho. So if I make delta s approach 0, I'm going to get the radius of curvature at the point that I'm trying to find. Okay? So I can use the chain rule now to write d theta by ds as d theta dx times dx ds, okay, where the x's here would cancel out. And that is going to be equal to 1 over rho, okay, where rho is our instantaneous radius of curvature. And now if I take this triangle here and then apply Pythagoras to that, so I can say delta s squared equals delta x squared plus delta y squared. And then I can rewrite that like this. If I expand this bracket here, so if I do delta x squared times 1, I'm just going to get delta x squared. And then if I do delta x squared times delta y by delta x squared, the delta x squared will cancel out, leaving delta y squared. Okay, so I've just rewritten this expression like this. So then I can rewrite that as delta s equals delta x times 1 plus delta y over delta x squared raised to the power of a half. So all I did was just square root this side. So that means I'll have to square root this term here. So I'm just going to be left with delta x. And then square root this term to be left with 1 plus delta y over delta x squared raised to the power of a half. And as you know, raising anything to the power of a half is the same thing as taking its square root. And then I can divide both sides by delta x to get this expression here. And then if I take the limit as delta x approaches 0 for delta s by delta x, I'm going to get this equation here. Okay, so ds dx equals 1 plus dy dx squared raised to the power of a half. So what I'm going to do now is take this equation here, I'm going to take this equation, I'm going to put them there. So now what I can actually say is d theta ds equals d theta by dx times 1 over ds dx. So all I did was inverse this. The inverse of ds dx will give us dx ds. So I've just rewritten this term like this. And remembering theta equals inverse tan of dy dx. So I can substitute theta into here and then take the derivative of inverse tan of dy dx with respect to x. So I've just taken this term, put it there, and then substitute theta with inverse tan of dy dx to get this. So because I've got a function of a function, I'd have to use the chain rule. So dy dx is a function, okay, it's a derivative, but it's also a function. So let's say, for example, if you took a function of x squared and then differentiated that, you'll get 2x. Okay, 2x is the derivative, but 2x you can also say is a function. So this dy dx you can say is a function. So we have a function of a function, so we need to use the chain rule. So there's the chain rule there, so I've got d theta dx equals dz dx times d theta dz. So z is the substitution I'm making, so I'm saying z equals dy dx. Okay, so I've substituted dy dx there with z, and then if I take the derivative of z with respect to x, and then multiply that by the derivative of theta with respect to z, I'll get d theta dx. So dz dx is just going to be d2y over dx squared. Okay, so I've got z here, and I'm differentiating that with respect to x, and that's just going to give me the second derivative of this expression, which is d2y over dx squared. Okay, so now I've got dz dx. Okay, so now I want to find the derivative of theta with respect to z. If we remember, theta here was inverse tan of dy dx, so I'm trying to find the derivative of inverse tan of dy dx with respect to z. But remember, we said dy dx equals z, so I've just replaced dy dx there with z. And then if I take the derivative of this, I end up with d theta dz equals 1 over 1 plus z squared. So then if I take this expression here, so dz dx and d theta dz and z over here, remember we're trying to find d theta dx, okay? So we found dz dx, right? So dz dx was d2y over dx squared, and d theta dz we found down here as 1 over 1 plus z squared. So if I just multiply this by that, okay, I end up with this. So remember d theta dx was just dz dx, which I found here, multiplied by d theta dz, which I found there, so I'll just multiply these two to get this. And then I can substitute z back into there to get this. Okay, so all I did was substitute z into here, and z was dy dx, so we end up with this over here. So remember, we're trying to find d theta ds, okay? So I know what d theta dx is now, so I found an expression for that, and I'll need to find dx ds. And remember we had this equation earlier on where we had 1 over ds dx equals dx ds. So if I substitute this into here, and I substitute this term into there, I'm going to end up with this. Okay, so d theta dx was this lot here, and ds dx was this over here. So I'll just multiply these two to get 1 plus dy dx squared raised to the power of 3 halves. And on top, that's just being multiplied by 1 to get that. And remember that is equal to 1 over rho. Okay, so d theta ds was 1 over rho. Okay, so now I can ignore this term here because I've got an expression here for 1 over rho. And then if I flip this side and flip this side, I'll end up with rho equals 1 plus dy dx squared raised to the power of 3 halves divided by d2y over dx squared. So this is our expression for the instantaneous center of curvature. Okay, so we write that down. So this is the radius of curvature at a point. We need to know the function of the curve. Okay, so we need to know f of x, and we need to know the x and y coordinates of the point the particle is. Let's take that curve again. So let's say this curve is defined by the function y equals f of x, and let's say we're trying to find the radius of curvature when x is, say, 2 or whatever. What we do is take the derivative of this function. Okay, so take that derivative and then evaluate that at x, and then substitute it into here, and then take its second derivative and then evaluate that at x again, and then substitute that into here. And then you'll find your instantaneous center of curvature at this point. Okay, so make sure you write this down, because next we are going to do some examples where we will apply this. So now we've looked at the introduction to circular motion, and we've looked at the normal tangential coordinate system. Now we're going to complete 3 example problems. Okay, so example 1. A particle travels at a constant velocity in a circular path that has a circumference of 126 meters. It then accelerates at a steady rate from 10 rpm, so revolutions per minute, to 40 rpm in 15 seconds and continues accelerating. Determine A. The amount of revolutions the particle makes when it reaches 40 rpm from 10 rpm. B. The distance travelled by the particle when it reaches 40 rpm from 10 rpm. The magnitude of acceleration of the particle at the instant it reaches 40 rpm. Okay, so we know that theta dot sub 0 equals 10 rpm, which is the initial angular velocity, so 10 rpm. And we know theta dot, the final angular velocity, equals 40 rpm, as given to us in the question. So first we want to convert theta dot and theta double dot sub 0 into radians per second. To do that, I do 40 rpm divided by 60 to get revolutions per second, and then I multiply that by 2 pi because there's 2 pi radians per revolution. Okay, so convert rpm into rps, so converting revolutions per minute to revolutions per second, and then multiplying that by 2 pi because I know there's 2 pi radians in every revolution. So if I do that, I get 4.19 radians per second. And if I do the same thing again for theta dot sub 0, I get 1.05 radians per second. So then I apply this equation here. So hopefully you had this written down. Okay, so theta dot equals theta dot sub 0 plus theta double dot times t. So I'm trying to find theta double dot. Okay, rearrange that for theta double dot there. Substitute our numbers in. So I knew theta dot was 4.19 radians per second. So substitute that into there. And substitute theta dot sub 0. I knew my time was 15 seconds. And put that into your calculator and you get 0.21 radians per second squared. So keeping that to one side there. So now I apply this equation here. So again, hopefully you had this written down. I'm going to say theta sub 0 is 0. So I'm going to say theta sub 0 is 0 because that is our initial angular position. So I'm saying that started off from 0. Okay, so I get this after I substitute my numbers in. So substitute theta dot sub 0 and time into here. Substitute acceleration into here. Substitute time into there. And I'm trying to find my angular position after 15 seconds. Okay, simplify all that down. So 1.05 times 15 gives me 15.75. And 0.21 times 15 squared over 2 gives me 23.625. Simplify that down, I get 39.28 radians. So that is my final angular position. So if I convert that into revolutions, I'll just do 39.28 radians divided by 2 pi. Because there's 2 pi radians in every revolution, and I've got 39.28 radians, so I divide that by 2 pi, and I get 6.25 revolutions. And that is my answer for part A. So to find the distance that has travelled, okay, so S is going to be the number of revolutions times the circumference. So I'm told the circumference in the question is 126 meters. So the circumference of the circle is 126 meters. And then if I multiply that by the amount of revolutions it makes, I'll get the distance travelled by the particle. Okay, so the revolutions was 6.25, times that by 126, and I get 787.5 meters. And that is my answer for part B. So now I'm trying to find the magnitude of acceleration of the particle at the instant it reaches 40 rpm. So the circumference equals 2 times pi times r. We know the circumference, and 2 pi we know, and we're trying to find r, so rearrange that for r, put our numbers in, and we get r as 20.1 meters. So now I use this equation here, so v equals r times theta dot, okay, and I find v, so v is going to be 20.1 meters from here, times 4.19 radians per second. So now I know the velocity, okay, and I get v equals 84.22 meters per second. Okay, so that is our velocity. And then I can find our centripetal acceleration by doing v squared over r, put my velocity into there, put the radius into there as well, and I get this. Okay, so that is our centripetal acceleration. So now I want to find my tangential acceleration, which is a sub t, which is going to be r times theta double dot. So we knew r, and we knew theta double dot, so put those in, put that into my calculator, and I get 4.221 meters per second squared. So that is my tangential acceleration. Okay, and then I can find the magnitude of acceleration by applying Pythagoras. Okay, so these should be squared. So an squared plus at squared and then square rooted. Okay, and then I'm going to get this. So 352.89 squared plus 4.221 meters per second squared, and then square root the whole lot, and I get this. So a equals 353 meters per second squared. And that is the magnitude of A. So that completes part C. Okay, so example 2. A particle rotates on a circular path from rest with a radius of r equals 10 meters with a constant angular acceleration of 5 radians per second squared. Find the magnitude and direction of the acceleration vector A after 7 seconds. If you want to have a go at this, pause the video now and get your pen and paper and just have a go, and then resume the video. Okay, so I'm going to apply this equation here. So theta dot equals theta dot sub 0 plus theta double dot times t. And then I calculate what theta dot is. So theta dot sub 0 was 0 because it said it started from rest. And I know the constant angular acceleration is 5 radians per second squared. Okay, So this term was 0, substitute theta double dot into there, and then substitute time into there, which I knew was 7 seconds. Multiply that to get theta dot equals 35 radians per second. And then we're going to use this equation here to find v, substitute my numbers in, so I knew r was 10 meters, theta dot was 35 radians per second, to get v equals 350 meters per second. Then I can find a sub n, which is v squared over r, substitute my numbers in, and I get a sub n equals 12250 meters per second squared. So now I can find a sub t, which is r times theta double dot. I knew r was 10 meters and theta double dot was 5 radians per second squared. Multiply them to get 50 meters per second squared. And then I can find a by again applying Pythagoras. So these should be squared. Substitute my numbers in again, and I get a equals the square root of this number here. And then I get a equals 12250.1 meters per second squared. And that is our answer for example 2. Okay, a particle travels along the curve with a constant speed of v equals 2 meters per second. What is the particle's acceleration when it is located at the point x equals 10 meters? Okay, so we have this curve here defined by this function y equals x squared. Okay, the particle is moving at a constant velocity along this curve, and we are trying to find what the particle's acceleration is at the point x equals 10 meters. A sub t is going to be 0 meters per second squared since the particle moves with constant speed. Okay, so the particle is moving along this curve with constant speed, so that means its tangential acceleration is going to be 0. So now we want to find the radius of curvature using our derived equation from earlier on. Hopefully you have this written down. If not, write it down now. Okay, so I know our function is y equals x squared. So find dy dx, which is going to give us 2x, and then evaluate dy dx at x equals 10 meters. So all I'll do is substitute 10 meters into there to get 2 times 10, which gives us 20. That is dy dx at x equals 10 meters. So I'll find the second derivative of this to just get 2. And then what I want to do now is substitute dy dx, which is 20 at x equals 10 meters, into here. Okay, to get that. And then substitute our second derivative down here, which is just going to be 2. Put that into my calculator, and I get rho equals 4015.01 meters. So that is our radius of curvature at x equals 10 meters. So now I apply this equation, so a sub n equals v squared over rho, put our numbers in, so I knew the velocity was 2 meters per second, and our radius of curvature we found, so just substitute those in, put that into my calculator, and I get a sub n equals 9.96 times 10 to the minus 4 meters per second squared. So find the acceleration magnitude, a, which is going to be the Pythagoras of a sub n and a sub t, so that should be squared. So I'll put those numbers in. Remembering a sub t was 0. So I'm just going to get a equals 9.96 times 10 to the minus 4 meters per second squared. And that is our answer for example 3. So if you found this video helpful and you would like to practice some more questions, then click the link in the video description, which will take you to this website here. Okay, or you can just copy and paste the link into your search engine like this. So that will take you to this home page, and if you click courses, engineering dynamics, okay, and you've got your formula sheet down here which summarizes all the equations that we found in this lesson. Okay, so that's going to be for normal tangential coordinates. Okay, so these are the equations that we found in this lesson, and you've also got a table of integrals and derivatives down at the bottom. Okay, so you've got trig identities there, derivatives, and you've got integrals at the bottom as well, down here. So you've got all the integrals. And if you click normal tangential coordinates here, you've got the same video here. So this is the video you just watched, and this is the PDF with questions that you can practice with. So question 3.1, 3.2, 3.3, and so on. And the answers are shown at the bottom. Okay, so these are the answers down at the bottom. And you've got the course content here as well. So these are just individual videos that answer each individual question on this PDF. Okay, so if you like to practice, this is the place to do it.